Hello everybody, my name is Ben Cranston and this is my homework 2. And this is a problem. I'm going to go ahead and get into it and I'll start explaining some of the basics of this problem to you. So, first off, we have a 10 centimeter long uniform cross-section capillary and it initially contains pure liquid, water, and deuterium on its left and right sides respectively. And this thing is 10 centimeters long. So the condition we're looking at is at t equals 0.1 seconds, the maximum molar diffusion flux was 2.78 moles per meter squared seconds. And then we have some information about the molecular weight and densities of both the components. And so part 1 is what is the overall mass flux at the maximum molar diffusion flux given. Part 2 is to make an order of magnitude estimate for the driving force at that flux. And then we're going to fill in some charts. So real quick, I'm going to go through and I drew a picture out down here to help kind of conceptualize this problem a little bit. This is the capillary. We start out and it's totally water on this side, totally deuterium on this side, and that's at 0 seconds. Then we give it 0.1 seconds and it starts to mix a little bit. We got some water over here, we got some deuterium over here, and there's some mixing in the middle, but only a little bit is mixed so far. And then we have H2O over here, D2O over here, and at 60 seconds, it's mostly mixed. There's still it's pretty much all H2O over here, and it's pretty much all deuterium over on this end. But there is some, there's some material that has gotten over all the way to either side. And then finally, at t equals infinity seconds, it's uniform. It's a uniform mix. So that's especially going to come in handy when we're looking at the charts. But yeah, that's just a good way to conceptualize this problem. So I'm going to go ahead and I'm going to flip this over. I'm going to go over to the projector and I'm going to start going over this. So I have the problem rewritten over here. And this is just a simpler version of everything I've told you with the really important details. And we're going to start going over problems 1 and 2. And I'm going to go ahead and cover part of this up just so we're not getting distracted by things that aren't relevant. So here's problem 1. We're looking for the overall mass flux at the given maximum molar diffusion flux. So we should actually go ahead and define a couple of those terms real quick. Mass flux is a mass, we'll say grams, per meter squared per second. So it's a measure of flow over an area. The molar diffusion flux is measured in moles per meter squared per second. And the diffusion flux is different from the regular flux because diffusion flux is a reflection of the flow that's the result of one component mixing or diffusing into another component. So that's when it says the maximum molar diffusion flux here is 2.78 moles per meter squared seconds. What that's really trying to say is each component is diffusing into the other component with that diffusion. Because the overall molar diffusion flux is going to be 0. And that's because each of the components are diffusing into each other. It's not like, water, if water comes from the left over to the right, one molecule of water has to displace one molecule of deuterium. This is a closed system. There's no flow in and out. So with all that in mind, we can say that there's no net flow in the system, no molar net flow. So we know that the molar diffusion flux of water is 2.78, and the molar diffusion flux of deuterium is negative 2.78. Now, why is deuterium negative? Well, deuterium is flowing from right over to left. Now, that's pretty important because we're using this negative to indicate direction, basically. So they have the same magnitude but different directions. So we're going to call this negative. And that's going to come in important later. So now we need to convert the diffusion flux to regular flux. So we have, this is the relationship between flux and diffusion flux for one component, for component I. So the molar flux of I equals the molar diffusion flux of I plus the concentration times the molar velocity. Now this second thing right here, that's called the bulk contribution. the bulk contribution only matters if there is a net flow in the system. And what I mean by that is that would be if like this were a pipe and there was flow all the way through the pipe. But there's not in this problem. So we can ignore this bulk contribution. And if you look down here, there's no net molar velocity. For every 1 mole of water that goes over here, 1 mole of deuterium goes over here. So the molar velocity is 0. We multiply that by 0, and we can ignore the bulk contribution, like I said. So that means that we're just left with the molar flux equals the molar diffusion flux for component I. So if we just plug in water and deuterium for I, we get, quite simply, we just bring it down. So with that in mind, let's convert the molar flux to mass flux. So here's that relationship. The molar flux, or this is the mass flux of component I equals the molar flux of component I times the molecular weight. And this is just very simply going from mass to moles. And how do we go from mass to moles? Well, we use the molecular weight. So that's pretty straightforward. And so if we apply that to these two problems, we will get that the mass flux of water is 50.04, and the mass flux of deuterium is negative 55.6. So think about this for a second. The mass flux of deuterium of that component is heavier or is larger than the mass flux of water, and you may have caught on. It's because it's because deuterium has a higher molecular weight, right? So we're multiplying by a higher number because the molecular weight is higher for deuterium. So for every 1 mole of deuterium that goes from the right to the left, well, that's more mass than a mole of water going from the right to the left. So that's pretty important. That's what's going on here. So we've got these two things. Now, how do we get the total total mass flux, or the total mass flux when we have all the components? Just go ahead and add them up. So we go ahead and we add them up, add up the mass flux of water, the mass flux of deuterium, and we get that the total flux, which is called N, is negative 5.56 grams per meter squared per second. So yeah, that is the answer to question 1. And let's go on ahead and look at question 2. So for question 2, we're looking at the order of magnitude for the maximum driving force. So I guess I should start out by talking about what driving force is. Driving force is a reflection of the strength of diffusion between two compounds. So that's kind of what driving force is reflecting as a number. So if we go ahead and look at the definition for driving force, we are going to see the definition for driving force for a multi-component system is this right here. But we are looking at a binary system. There's only 2 components, which instead of having to deal with this whole summation, we basically can just cut the summation off because we're only looking at one term of the summation. That would be this term. So we can go ahead and cut it off. And because the driving force, similarly to how the diffusion fluxes of water and the diffusion fluxes, we talked about it up here, diffusion fluxes of water and deuterium are just going to be equal and opposite to each other. We're just going to call the driving force D. That's just what we're going to call it because it's not really for either component, it's just for either, it's not for either component specifically, it's for either component. So we're going to look at, that's the molar fraction of component I times the molar diffusion flux of component J. So it's 2 different components being multiplied minus the inverse of that. So the inverse of that would be the molar diffusion flux of J times the molar diffusion flux of I. And I meant the mole fraction. And then on the bottom we have the concentration, the molar concentration, and then we're going to multiply that times this D, and this is the Stefan-Maxwell diffusion coefficient. And this is just a reflection of how well the 2 fluids mix, basically. So we go ahead and we're going to take a relationship, because this is a binary system, we know that component I is 1 minus the component J. We can plug that in, and we know that because the diffusion fluxes are equal and opposite, we can use that, and we can basically cancel out a lot of this nonsense up here on top. So that just leaves us with the negative molar diffusion flux over the molar concentration times the Stefan Maxwell diffusion coefficient. So if we go back up to the top, we know we're looking for an order of magnitude, right? Well, we can kind of memorize the order of magnitude for a liquid just from approximation, basically. Just from experiments, the order of magnitude for any liquid is going to be 10 to the 9th for the Stefan Maxwell diffusion coefficient. That's just something we can memorize. It's determined by experiments. And yeah, so that's just what we're doing there. Now, if we go down here, you see I've got the molar diffusion flux written out, so we're going to plug that in too. And here, we've got this too. This is saying the molar concentration equals the total mass of the system divided by the total volume of the system. Now we're doing this under the assumption that the total volume of the system is 2 meters cubed, and each side basically has, the water side has 1,000 kilograms of water, and the deuterium side has 1,110 kilograms of deuterium. We multiply it by the molecular weights for each corresponding one to get a mole on top, and that just lets us find mole fraction, moles per volume. Pretty straightforward. So now we're going to kind of plug all this in, and when we plug it all in, we can solve it all out, and we're going to get that the driving force is 50,065, and we'll just go ahead and round that down to about 50,000, and that's kind of the order of magnitude. The order of magnitude for the driving force is about 50,000. So yeah, that's what we got going on, and I will go ahead and get this shifted around, and we'll take a look at part 3, which is filling in some charts. So this is question 3, and what we're looking at here is we're gonna create graphs reflecting the density, the molar concentration, the molar diffusion flux, and the mass flux down here. Sorry, that got a little bit cut off. In 3 situations. And these 3 situations are 3 situations we kind of talked about before at the beginning. This is the time is 0.1 seconds, so right as it starts mixing, or the initial, the intermediate, so that would be t equals 60 seconds, or the final, which would be t equals infinity seconds. So if we go down here, we'll get a little reminder. There is very little mix initially. Then this is a partial mix, so I guess I should draw this out a little bit more. We're saying that at 60 seconds, the water and deuterium is all the way spread out. There is some water, there's some deuterium all the way over here. There's some water all the way over here, but it's not fully mixed yet. And then in the final situation, t equals 60 seconds, this is going to be uniform down here. So that's something we got to look at first. So I'm going to go ahead and I'm just going to look at the whole 0.1 second situation. I think it makes more sense to explain it that way personally. I think that just makes more sense to talk about it that way. So, yeah. Let me get it zoned in real quick. Unfortunately, if you couldn't see everything. And so, yeah, here is this. So we're looking at the density of each component here. So at 0.1 seconds, we know that the density of water is going to be what this is saying is that there's pretty much all water for the first 4 centimeters or so of the system. Then, all of a sudden, it's going to drop down really quickly, and it's going to be pretty much all deuterium in the last 4 centimeters. And there's really only mix in the middle 2 centimeters of the capillary. And then if you look down here in molar concentration, it's something very similar. Very similar thing is reflected. Now, if you notice, the big difference is that deuterium has a higher density than water. So that's why deuterium's line is higher than water, because deuterium has a higher density. That's just given in the problem. But the molar concentration, they're about the same. Now, why is that? Well, there's some math that we can look at. And so here's calculating the molar concentration of pure liquids, water, and deuterium. So let's take a look. We start out with the densities of each. Start out with the density, multiply by the molecular weight, and then I adjusted here to turn it from meters cubed to meters. And we're going to see that they give about the same number, which this makes sense, that their concentrations of these 2 things would be approximately the same. And that's really because these are two very similar components. And I realized I mixed something up right here on my piece of paper. That should say deuterium 2 oxide. I wrote that down incorrectly. It's shown clearly right here. So yeah, they're very similar because ultimately the only difference is there's 2 extra neutrons on the hydrogen. So it's not making a huge difference in any of the properties of, or at least in the properties we're looking at here. I'm sure there's some properties that are very different between water and deuterium, but we're mainly just looking for the concentration. It's not going to be that different. So yeah, going back to the chart, and we're going to go ahead and look, and we're going to see the molar diffusion flux. So we notice that on these sides it's 0. So remember, the middle of the chart is 0 here. And then it goes up really high in the middle for water and then really low on the bottom for deuterium. That's because the middle is the only place where there's actual mixing going on. So there's only diffusion going on in the middle. You put the diffusion is 0 out here because it's just water out here and it's just deuterium out here. So it's all, we could look at it down here. It's all deuterium, it's all water. There's no mix. So yeah. And then down here, the mass flux. So you have to remember, the overall mass flux of the system is going to be negative while it's mixing. And we know this because deuterium deuterium is heavier than water. So if 1 mole of water goes over this way and 1 mole of deuterium goes over this way, well, overall the mass has gone this way. So we know that the mass flux is going to be negative, at least in the areas where it's mixed, but it's only mixing, it's not fully mixed. So these parts still don't have a mass flux because the mass hasn't changed. It's all water, it's all deuterium. So let's go on to 60 seconds. 60 seconds, you're going to see that there's already water, there's already deuterium that's made its way all the way over to the left, and there's water that's all the way over to the right, down here. Water all the way over to the right, deuterium all the way over to the left. So you won't be surprised to see that the density of water is not, it's not completely water over here. So it's going to be less water, and a little bit of the density comes from deuterium over here. But then over here, you look at the deuterium. I've said that word so many times, it's all kind of just blurring into one thing. And you see that there's a lot more deuterium than there is water. So then we look ahead down here, and we see for the molar concentration, this is just kind of a cleaner version of the graph I drew out over there. But you see it's not fully water. There's still some deuterium all the way over to the left, and the vice versa on the right. And it kind of intersects in the middle. But the concentrations are so similar, they're basically the same. Now you look down here, and you see that the water, now because there's mixing going on everywhere in the capillary now, even though it's predominantly mixed in the middle, there is still the most flux in the middle of the capillary, but there's flux, there's diffusion flux going on all the way out to either end of the capillary. And obviously, the diffusion flux for H2O is positive, the molar diffusion flux for D2O is negative. That's just because of the direction these two things are flowing. Then you look down here at mass flux, and you see there's mass flux in the middle, but it's negative because once again, mass is flowing from right to left. So we're going to label that as negative. Another quick thing to note: the peak here is lower than the peak here. The peak here is lower than the peak here. That's because this is the maximum diffusive flux was recorded at 0.1 seconds, not at 60 seconds. So it's going to be less here. It's going to be less for any point after that. So yeah, and finally, situation, it's totally uniform, right? So in the end, this is at T infinity. It's totally uniform, right? So there's now more mixing going on. So we're going to look at this, and we're going to see, well, what are the densities? Well, the densities are going to be pretty uniform. There's, D2O is going to have a density of half, because there's half a mole per liter now, and H2O is going to have half a mole per liter too. So it's going to be, I think that says 555 for deuterium and 500 for water, and that would be in moles per liter. Sorry, that would be in kilograms per meter cubed. This is in moles per liter, but because the concentrations are so similar, I just drew one line They are going to be slightly different on like a very, on a very low level. Consult the math I talked about earlier when I solved for the concentrations. And so yeah, now the molar diffusion flux is going to be 0 now for both, because there's no more mixing going on. They're fully mixed. There's nothing else changing in the system. And finally, the mass flux. The mass flux is going to be 0, because even though the net mass flux, there's no more mixing going on, so there's no more change. And so the rate, because once again, flux is a rate, the rate is 0. There has been a net shift in the center of mass. Initially the center of mass is probably like, we could say maybe the center of mass is right here. Now the center of mass is in the dead middle of the system. But now the mass flux is 0 because there's no more change in it. So yeah, that about covers everything on here. I'll try to get a good wide shot of this for you to see. I appreciate you taking the time to look through this, and I appreciate any input or comments or anything else. And I hope you have a nice one. Thank you.